This conference will now be recorded.
So very good evening. Today it will be the last class for this particular topic, system of particles and rotational motion. We have been learning this chapter very in detail for so many days. Today we'll be finishing off with learning few very important topics today, like rolling motion and rolling down in an inclined plane. So when an object is rolling down in an inclined plane, what will be the velocity and what is the condition? The most important question will be that what is the necessary condition for a body to incline to roll down without slipping? So that condition we have to find out. Okay, so those things we'll be doing, and if time permits we'll take a few numerical examples. So before I go to rolling motion along an inclined plane, let me just recap what we have learned. Simply, rolling motion. So when rolling motion occurs in a plane surface, what happens? We can consider rolling motion as combination of two motions. One is rotation, that is pure rotation. So it is combination of pure rotation and pure translation. I'll tell you what is pure mean, what I mean to say by pure. Okay, so pure rotation means only rotation will happen. There will be no mixed motion or combination of any motion. So in this case, rolling is actually combination of these two. So this is not a pure motion, neither a pure rotation nor a pure translation. So rolling motion is a combination of pure translation and pure rotation. Okay. Now what I'll do, I'll take up, see this example in this figure. This is a disk. Okay. Suppose this is a disk, and so suppose this is a disk, and the disk actually is rolling on a plane surface, plane horizontal surface. See, the common example for rolling motion is the motion of any kind of wheel. Take bicycle, cycle, car, bullock cart, whatever you take, horse cart, whatever you take. So rolling, the perfect example of the rolling motion is motion of any wheel. So I am taking a disc which has a symmetry of wheel only. So suppose it is moving on an horizontal plane, and the angular velocity of rotation is omega. Okay. Now look, in this case, when this disk is rotating, at the same time the center of mass of this disk is actually translating along this line. You see this one and this one. If you just add this line, so this line is parallel to the plane surface or horizontal surface. So this is, so along this line the center of mass moves in the forward direction. So you look, it has see the center of mass has pure translational motion. Center of mass has pure translational motion, or I'll discuss in the next slide. The translational motion is described by the motion of the center of mass itself. Okay, and look, if I just consider this particular point, this particular point, okay, it is, see, it is going all the way from here. Okay, it goes to top here and then goes down. That means when it was at this particular position, and in the course of motion it goes top and then comes back to bottom with contact like with contact of the horizontal surface. So when is actually it is making a complete rotation, then the center of mass, it moves by a distance 2 pi r. Okay, 2 pi r. So this is the distance. In general case, center of mass cover for a complete rotation of a wheel. Here it is, r is the radius of this disc. Okay, this is the thing we know since our 7th standard or 8th standard onwards. We know this. Now one more important thing we'll see here is that rolling without slipping. Rolling without slipping. Without slipping. See the condition, like what I have shown here. The center of mass is moving a distance 2 pi r upon a complete rotation. This happens only when rolling motion is happening without slipping. That means what? The point of contact. See the disc, for the disc, this is the point which is the bottommost point, is in contact with the horizontal surface upon which it is rolling over. Okay, which it is rolling over. So this point of contact is not moving. Momentarily it is rest. It is at rest. At each and every instant, whatever point of this disc, whatever portion of this disc comes into contact with this surface, that becomes momentarily rest. Okay, so this is the condition for slipping, sorry, rolling without slipping. And that condition, the center of mass upon a full rotation moves 2 pi r distance. Okay, so now we'll see what happens in this kind of rolling motion. As I was showing that it is a combination of translation and rotation. So how to describe the translational motion of this disc? Translational motion of the disc will be described by the motion of the center of mass. That means if you take anywhere, any point on this disc, any point on this disc, if I know the motion of the center of mass, I'll take the motion of each and every particle on this disc as identical to the motion of the center of mass. And this is the disc by symmetry. The center of mass will be at the center, geometrical center, as you see here, capital C, we have denoted here. Now, let us say the velocity of the center of mass, as we were seeing in the previous slide, the center of mass moves parallel to the surface. Okay, parallel to the surface. and it is moving in the forward direction. So let us say the velocity of the center of mass is v cm or com, whatever you can write, vcom or vcm, you can write whatever you like. I have written here vcm, but in the figure it is written as vcom. Doesn't matter, both are the same. Now if I consider the translational motion of any particle, the velocity, translational velocity, okay, of any particle will be the same as this vcm. Okay, all right. Now let us see. Okay, this will be rotational motion. Okay, this will be rotational motion. Now we'll see the rotational motion. So rotational motion, the disk rotates with angular velocity omega about its symmetry axis, which is passing through the center. Passing through the center. See. So if I consider any arbitrary particle, okay, any arbitrary particle at, suppose this is p2 distance, okay, p2 distance, okay, suppose that, sorry, p2 point, suppose I consider any particle or any point of the disk as p2, okay. So p2, since it is rotating as well as translating, this p2 point will have both kind of motion, translational motion as well as rotational motion. So we know vc will be able to, we know that translational motion, if translational motion is v or translational velocity is v, the rotational velocity, we know the we know the relation between rotational and translational velocity, that is v is equal to r omega. If the r is the distance of that particular particle, if I say this is at a capital R distance, suppose this is moving with omega. Omega is actually the angular velocity of all the particles on this disk. So the rotational velocity will be v is equal to r into omega. Okay. Oh, sorry. This is actually the velocity, translational velocity due to rotation. This is actually called translational velocity due to rotation, or linear velocity due to rotation. Okay. So this will be actually linear velocity due to rotation. V is equal to, v rotational is equal to r omega if the r is the distance from the axis of rotation. So in this case, look, the axis of rotation is actually the center of, like passing through the center of mass. So in this case, we have considered the P2 point. Suppose P2, it is at r distance, okay, r2 distance away. See, this is the r2 radius, so it will move like this, okay, in a circular path having radius r2. So we can write v p2 rotational, due to rotational motion will be r into omega, r2 into omega, okay, r2 into omega. Now see, this velocity will be always perpendicular to the radius. See, cp2, this is the radius, which is r2. See, this vp2 in the sense, rotational, like linear velocity arising due to rotation will be always perpendicular to this r2. So look, this one is the velocity and this is the angle perpendicular. You can see this here. I'll clean it up here. Look. So omega into r2 or r2 into omega, this is the velocity of this particular point due to rotation. Okay, r omega 2, which is perpendicular to this r2. Okay, this is what has been shown here. Okay. Now look. So we are saying that rolling motion is combination of both rotation and translation. Then what will be the total velocity or resultant velocity? See, the VCM is along this direction. So I have got two things here. One is V rotational, okay, which is R2 into omega, okay. And another velocity we have got this one, VCM, okay, VCOM or VCM, whatever you write. So what will be the resultant? It will be the sum. This will be actually the sum of, suppose VP2. This is the actually VP2. This is sum of the these two or resultant of these two velocities. One is the linear velocity arising due to rotation and another one is due to translation. So combination of these two velocity R2 into omega or omega R2 plus VCM, okay, VCM or VCOM, this will give you the resultant velocity of this particle, okay, P2 particle due to rolling motion, due to rolling, okay. So now similarly, if we consider the motion of this P1 and this P is 0, P1 is the topmost point and P0 is the bottom point. Let us see. P0, since this guy, this point, as I said, this is rolling without slipping, rolling without slipping. That means rolling without slipping means this P0 must be having velocity 0, resultant velocity 0. Okay, this should have a resultant velocity 0 because due to rotation and translation there will be two velocities. So look here, see it is having velocity due to this CM, VCM, like cancellation motion of the disk, that is VCM, and the rotational velocity of this particular point must be in the opposite direction and exactly equal to the velocity of the center of mass. So that's why in this case the condition for rolling without slipping is given by, see, given by R omega is equal to VCM, okay, or VCOM. Here it is written VCOM, or better I'll write VCOM only. Okay, so VCOM. Okay, so R omega is equal to VCO. R omega is in this direction as you can see here. Why R? Because this is the radius of the this CP0. This is the radius of this disk, and this is the VCM, which is in the forward direction. This is in the backward direction. They are equal in magnitude. Equal in magnitude. So that's why look, this is the condition. Okay, VCOM. Okay, this is the condition for. So I'll just write it here. Condition for slipping, sorry, rolling without slipping. So what is the condition for rolling motion without slipping? Condition for rolling without slipping is VCOM is equal to R omega. So this has to be satisfied. So whenever we will be seeing in the numerical problem that the motion is happening, rolling motion is happening without slipping, then we can use this condition to have a relationship between the translational motion and rotational motion. Okay, so this is what we had to know here. Now we will see what is the velocity velocity of this top point. See this top point P1, it is moving forward direction, right? So it has velocity due to rotation and translation both. Due to translation it is VCOM as you see, and due to rotation it has R omega. So it has R omega plus VCOM. Okay. So I'll write. So the resultant of this will be R omega plus VCOM, and if you write this as R omega VCOM, because if we use this condition VCOM is equal to R omega, then it will be 2R omega. So it has actually 2R omega velocity. Okay. So this is the condition here. So this was this side, whatever we have done, this thing, these are actually rolling without slipping with this condition, holding this condition VCOM is equal to R omega. Now we can have two special cases of rolling motion. What are those? Look, I have written down. This is one condition. So what does this mean? See, in general we have seen the center of mass. So I'll take up the first condition that VCOM is greater than R omega. So what is this condition? See, in general, a circular wheel or disc or whatever, due to rolling without slipping, the center of mass covers a distance 2 pi r for a full rotation. Okay, for a full rotation. But suppose due to some reason the distance is covered is greater than 2 pi r. Okay, so COM, the center of mass which is covering a distance for a full rotation, if it becomes greater than 2 pi r, so if it becomes greater than 2 pi r, what does that mean? If this becomes greater than 2 pi r, it actually automatically means that the translational motion is happening greater than r omega. Then this is no longer valid. So this is the condition. So when motion happens, like the translational motion is happening much more than rotation. I'll give you a simple example. Suppose you are riding a cycle, and after the rain you are going through a road, and the road after rain becomes very smooth, and you wanted to stop the cycle by applying brake. So in that case you will see after applying brake, it is not immediately stopping. It will be actually see the contact point, your wheel will be somewhat rubbed over the road, and it goes some up to some distance. Okay, it goes up to some distance and then stop even if you apply the brake. So as soon as you apply the brake, what happens? The rotation stops almost. Okay, that means rotation is not happening. Rotation is not happening, but translation is happening. So this is the condition. Okay, this is the situation where you can cover, your center of mass covers a distance greater than 2 pi r, and your translational velocity will be greater than the rotational velocity. Okay, so this is the condition BCM. This is one of the special cases. So this is called first, just a minute, it is called fast forward motion, or motion translation. Translation is okay, so it is actually, see, in this case it was without slipping, but here actually with slipping. Okay, with slipping, your contact point is slipping. Okay, slipping over the smooth road. Now I'll give you another special case, that is the condition 2. See, see from the condition 2 you can just imagine that or you can understand that VCOM is less than R omega. That means your translation is less. Translation motion is less than rotational motion. Can you give me an example of this where rotation becomes more than translation? Yes, we can give one example. So in this case, your translation happens less. So that's why your distance will be actually the center of mass will cover a distance or path less than 2 pi r. Less than 2 pi r. Okay, I'll give you an example, very simple example. Suppose you are riding a cycle, same cycle on a muddy road. On a muddy road. Okay. Sometime you may make or you may apply many paddles. Okay. You may rotate your paddles like anything, but rotation happens very less. Rotation happens more, but your translation happens very less. You are not moving forward. Your whereas your wheel is actually rotating very fast, but VCM, the center of mass, is not at all moving. Okay, so this happens in the muddy road. Okay, in the muddy road, you have to make many rotations when your center of mass moves a little. Okay, so that's why this condition is. This is actually motion with actually more translation. Here, more translation than rotation. Translation than rotation. Okay, than rotation. And this case, more rotation than translation happens in the muddy road. Oh, sorry, more rotation than translation. Okay. All right. So with this, I have finished this part. Now we'll go to the rolling motion along an inclined plane. So suppose I have an inclined plane or I have a plane. This plane you can see which is inclined at theta angle with the horizontal. Now I have taken a cylinder. Okay, a cylinder is rolling down, rolling down without slipping, without slipping. Okay, without slipping. So we know in case of inclined plane there will be multiple forces acting. We'll see what are those, and we'll try to break the components out if necessary. So look, this is an inclined this is an inclined plane which has inclination angle of inclination theta, and I have a cylinder of radius r. So cylinder has radius r. Okay, suppose this has cylinder has radius r. Okay, a cylinder having radius capital R. And you see, in case of horizontal motion, disk, like without slipping, only one point was fixed, and rotation was happening through the center of mass. Okay, so now look, in this case, when it is rolling down, cylinder is rolling down. Actually, cylinder will have a contact line rather than having contact point. It will have contact line, and that line will act as axis of rotation. That contact line about which this will be rolling down. Okay, rotating. So it has both rotational motion and translational motion, since it is a rolling motion. Okay, rolling motion means there will be both. Rolling is happening about an axis which is actually passing through the contact of this cylinder, that is actually a line which is acting as axis of rotation. Okay, now so that line goes through this contact point, suppose P. Now I'll do one thing. I'll just first break the component of the forces and we'll see what are the forces responsible for rotation and what are the forces responsible for translational motion. And then we'll try to find out, according to Newton's second law of motion, I will try to write down the equation of motion for this cylinder. So look here, as you can see from the figure itself. So this cylinder has certain mass, so the weight will be actually acting vertically downward to this horizontal surface. Okay, not vertically downward to this inclined plane. It is always vertical, always perpendicular to the horizontal or the ground. And look, if this angle is theta, then obviously this particular angle also will be theta. We have proved many times how this becomes theta. Anyway, now you consider this is theta. So we can just break the components of this weight. Okay, weight mg, I can break a component which is along the perpendicular direction, perpendicular to this plane, and this is actually acting this way. As you can see, this is cos theta component. This is cos theta component mg cos theta, which is acting perpendicular to the inclined plane. And the other component mg sin theta, it is acting along the inclined plane and in the downward direction. As you can see, mg sin theta acting along the inclined plane and it is parallel to the inclined plane. Okay, now see, here normal force also will be working because this cylinder is in contact with the inclined plane. So the normal force will be depending on the plane or contact surface. If the plane is this way, so it will be in this way. If the plane is this way, then normal force will be this way. If the plane is this way, then normal force will be this way. Okay, this is the contact force or the normal force that becomes always perpendicular to the contact surface. So that's why this force will be perpendicular to the inclined plane. Okay, so now then we have some forces. So I'll write first force is mg weight. Okay, acting vertically downward, vertically downward. Okay, then second force is actually normal force acting vertically upward vertically upward to the inclined plane. Inclined plane. Okay, and the third force, that is the friction, which is actually satisfying this condition. Okay, so this is what actually making the rotation of the, so the frictional force, friction. Okay, friction which is responsible for rotational motion. Friction responsible for, you have to understand this. This is very important. You might be thinking who is giving the torque to this cylinder for rotation, responsible for rotation. That is the responsible for rotation. This friction is responsible for rotation, whereas mg sin theta, this is actually responsible for translation. Okay, that we have already learned in case of work power energy, and before that also we have learned. So mg sin theta actually responsible for translation motion. I'll just write here. So translation, responsible for responsible for translation, and this is the guy which is responsible for rotation. So this, if you know this, then half of the concept is learned. Now you have to do certain calculation. Okay, so this is what the thing. Now what we'll do, we'll just go to the next slide and see, according to, see, it is rolling, right? So it is actually going down. So both translation and rotation is happening. I'll just consider the translational motion first. Translation first, motion. Okay, let us take translational motion. So which is happening along the direction of, like along the inclined plane, and it is downward direction. So according to Newton's second law of motion, what we can write is, see, I say net force downward. Okay, that's why it is rolling down. So translation is, so net force downward along along the inclined plane. What it is? It is, look. So F net I am writing like that. So I will just writing here. F net will be, so this is the force mg sin theta due to gravity, and another force is this one. Okay, the the net, see, the resultant force of these two will give you the translational motion. Okay, now what we'll do, we'll try to find out what is the frictional force. Okay, so what is frictional force? So this F net, let me write this F net. Suppose the cylinder has mass m, capital M, so it has mass, or small m, let me take that as small m, since I have taken there in the small m. So small m into a is the acceleration along this direction. Okay, so m into a will be the resultant of these two forces. Now we'll try to find out. So this, let me take this as equation number 1. Now I'll just try to find out what is giving the torque. I have told you that this frictional force, frictional force is actually responsible for giving torque. So torque will be, see, frictional force is acting this way, right? So torque, and it is rotating. Suppose it is rotating about its cylinder, like axis of rotation, own axis of rotation. So what is the torque? F into R. Okay, so F into R is the torque. All right, this is in terms of like scalar quantity. It is, now I am writing this as scalar notation. Now look, this torque, we know there is a relationship between the angular acceleration and, see, if I write F into R over here, sorry, torque is equal to, see, F is equal to tau by R, torque by R, then I don't know this what is torque. Then I have to convert this into some known term. So look, this tau, we know, we can write this as I into alpha. This I is moment of inertia. So torque is equal to I into alpha, where I is moment of inertia, moment of inertia, and alpha is the angular acceleration. Okay, angular acceleration. So this is how we can write. So I can write this then. F is equal to I into alpha can be again written as in terms of C, since here I can write m into a. So if the a is the linear acceleration, then I can write this alpha in terms of linear acceleration. See, alpha is equal to, see, linear acceleration always given as a. If this is linear acceleration, then it will be r into alpha. So alpha will be a by r. So if we put this, look what we get. This frictional force will be I into a by r square. A is the linear acceleration. So I'll just clean this portion and let me write this very clearly what we have got. See, we know this is the equation of motion where we have to put the value of frictional force. Let me keep this. And what is the frictional force we have got? We have got frictional force as I into a. A is the linear acceleration of this divided by r square. Okay, so these are the things I have got. Now what I'll do, I is the moment of inertia, so we have written here. You can just have a look over here. So we can just, this is 1, so we can have this 2. So if we put this 2 into 1, so what we get is m into a is equal to mg sine theta I into a by r square. Okay, now we'll just do one thing here. A is equal to mg, sorry, m will go away, so it will be g sine theta minus I into a by m into r square. Okay, so this is what we get from here. Look, this is another equation which is important to note. This is, let us say, equation number 3. Now I'll just remove this portion as I was saying that I is the moment of inertia. Now look, if we write the moment of inertia of this particular cylinder about its own axis, so what will be the moment of inertia? Okay, before that, let me okay let me let me not giving, okay, let me do little bit more simplification, because both side there is a. I'll just do a simple, see, I'll just take this common and I'll take this part away here, left hand side. So this is m r square, this will be equal to g sine theta. Okay, one more step I'll do here. So write a. A is the acceleration, so I can find out what is the acceleration. So you can see, you can finally get the force which is responsible for only translation. That is, see, this is the acceleration, so if you multiply with them you will get that. Look here, g sine theta divided by 1 plus I over m into r square. So r is the radius of the cylinder, m is the mass of the cylinder, I is the moment of inertia of the cylinder about its own axis. So if it is happening about its own axis, then what happens? Let us say this is actually, uh, yeah. So this is a solid cylinder. Also, you have to remember that. So it will be actually m r square by 2, just like just like a just like a disk, m r square by 2. So if we put this over here in this equation, this suppose this is 3, equation 3. So I'll just do one thing. I'll repeat it once. See what we have done, how we have got this equation 3. We had written equation of motion from this, okay, using Newton's second law of motion. A is the linear acceleration I have supposed, and see, I had to write what is the value of F. F is the frictional force. Okay, and what my agenda is here, here to find out what is the force responsible for translational motion. So that then if you somehow can calculate the acceleration, then you will get the net force in that direction. So I am doing the same thing here. So to do that, F is actually the frictional force which is giving the torque. So torque will be F into R tau, and tau again can be written as I into alpha. From there we have written, see, alpha can be again written A by R. So I have got F is equal to A, I into A. I is the moment of inertia of that particular object. Here it is cylinder, solid cylinder. So we have got what is frictional force in terms of A and R. So this we will be putting into equation 1 and simplifying that. Upon simplifying, what we get is this equation number 3. So in between this steps I'll be clearing out, and I'll write that equation number 3 at this place. Okay, so I'm just writing here g sine theta 1 plus I over small m into r square. Okay, this seems to be very critical. No, if you just do this with patience, then it will be all right. You can solve this problem. So now what I'll do, I'll just calculate the moment of inertia of this cylinder about its own axis. So look, this is mr square. It is small m here. So mr square, if we put here, what we get is 1 plus mr square here, mr square by 2. So mr square by 2, I'll write down. Mr square was already there. So you see g sine theta here. You can see that mr square. So what you get, it will be 1 plus 1 by 2. So it will be actually 2 by 3 g sine theta. So this is the acceleration you get for for translational motion, and this is actually giving you an acceleration of a rolling body. Especially in this case, this is the solid cylinder. See, for a cylinder, it has acceleration along the inclined plane, which is less than g. You can see that this is less than g. Okay, less than the gravitational acceleration. Okay, this is less than gravitational acceleration. One more point you can note here. See, it depends. See, for a particular inclined plane, it doesn't depend whether the object has greater radius or greater mass or whatever. It does not depend on mass and radius. Okay, it does not depend on mass and radius, but obviously it depends on the nature of the object or shape of the object. Suppose in place of solid cylinder, so we have got the acceleration for solid cylinder as 2 by 3 g sine theta. This is an important outcome. Okay, if I would have taken hollow cylinder, then what would have happened? Okay, for a hollow cylinder, this moment of inertia will be mr square alone. If we put it here, see, a will be g sine theta, okay, divided by 1 plus mr square. I will be mr square, and this is also mr square. So this will go off. This will be becoming 1. So finally you get g by 2 sine theta. So it becomes again less. Okay, it becomes less. That means if you have been given a solid cylinder and hollow cylinder, which one will roll down first? Because the acceleration is more in case of solid, then solid will be actually rolling down fast. This is for solid is greater than acceleration for hollow. Okay, acceleration of the solid will be greater than the hollow one. So that's why hollow one will be moving down later than this solid one. So I'll clean up everything and I'll write down whatever outcome I have got so far. So I have got, due to translational motion, like for translational motion, I have got g sine theta. This is the acceleration I have got. G sine theta is equal to 1. Okay, sorry, a is equal to g sine theta over 1 plus I over m r square. I is the moment of inertia. Okay, this is what we have got. And one more thing, we have got F is equal to I into a by r square. This is what we had got. This is equation number 3. This we had written equation number 2. And the first equation I'll be writing, that is m into a is equal to mg sine theta minus f. Okay, f. So now my agenda will be to find out what is f. Okay. Now see, f is this much. Okay, if I put it here, the value of a, then I should get the value of f. Okay. So this was equation number 1 in fact. So I'll just do from here. Let me see how we get. So f is equal to mg sine theta minus minus m into a. So mg sine theta I have here, and see a is this much. So I'll just, in this case it was, see in case of cylinder it was a is equal to 2 by 3 mg sine theta. Sorry, g sine theta, a was g sine theta. Okay, so m is already there, so I can just write it 2 by 3 m into g sine theta. Now if we just do this simplification, look what we get is 1/3 mg sine theta. And see, normal force what we have got, since there is no vertical motion, so normal force will be equal to mg cos theta. So from here we can find out what is the necessary coefficient of static friction which will help you to have rolling motion without slipping. Okay, what is the minimum value of that static coefficient of static friction? So you know this is f by n. So what is f? F is 1/3 mg sine theta, and this you know mg cos theta. So this goes off, so you get 1/3 tan theta. Okay, so this is the minimum value of static friction, like coefficient of static friction you should have. Okay, for the inclined plane to have rolling motion without slipping. That means I'll write on the right hand side. Let me just clean this up. So to prevent the slipping, so to prevent the slipping, the coefficient of static friction must be equal to must be equal to or greater than 1/3 tan theta. Okay, if we write in terms of mathematical language, so it has to be like this. Okay, this is very important question for many competitive exam. Okay, or or in other words it will be given in terms of this tan theta less than or equal to one third, sorry, this will be 3 mu s, 3 mu s, less than or equal to 3 mu s. Either of these two forms will be asked in your exam, okay, competitive exam. So this is how rolling happens without slipping. This is the condition for rolling without slipping. Now I'll just take up one more thing here. So suppose an object, I'm taking the same figure, I'm just trying to find out what is the total total kinetic energy, total kinetic energy of the rolling motion, kinetic energy of rolling motion, rolling motion. Especially we'll take, see, in any rolling motion the total energy will be rotational kinetic energy plus translational kinetic energy, okay. So this is what we are trying to calculate, and then we'll just see in case of inclined plane there is a simple problem, okay. So we'll take up that. So total kinetic energy will be, I'm writing kinetic energy as, let me write that ek, total rotational kinetic total kinetic energy is equal to ek rotational, okay, plus ek translation, okay. So rotational we know, translation, let us write first what is translation. Translation we know half m v center of mass square, okay, square of v velocity of the center of mass, square of the velocity of the center of mass, okay. And this is actually, see, this mass is actually like omega is equivalent to mass. So I omega, sorry, I is the moment of inertia, which is actually equivalent, or yes, equivalent to the mass in the translational motion. So moment of inertia is actually equivalent to mass in the translational motion, so it will be half I omega square. Now look this, we can do little bit of simplifications. As we know, for motion without slipping, so if without slipping, then we know vcm is equal to r into omega, okay. And then let me consider k is the radius of gyration. If k is the radius of gyration, if k is radius of gyration, radius of gyration, then we can write I is equal to mk square, okay, mk square. We can write I is equal to mk square. This is the definition of radius of gyration. What is the definition of radius of gyration? We have learned radius of gyration is actually a geometrical distance or point from axis of rotation, okay, of certain distribution of mass, okay. You take a point as if the whole mass is actually concentrated over here, and if we take the moment of inertia mk square, okay, this is the distance from, k is the distance or geometrical point where the whole mass supposed to be considered, okay, supposed to like considered to be concentrated. So we can write moment of inertia as mk square, and in fact according to the definition it is, so like if it has different distribution of masses, if you calculate the moment of inertia taking the true distribution of masses, and if you take a point on that particular object, and if you calculate the moment of inertia with respect to that, both become same. So according to that definition, moment of inertia can be written as mk square if the k is the radius of gyration. So I'll just replace these two equations. So VCM I'll be replacing with R omega, and I'll be replacing with mk square. So let us do that. Okay, so yeah, maybe I'll just, for the timing, let me keep this VCM square as it is. I'll just change the I omega square term. Half omega square, let it be this as mk square will write. Okay, so omega is again, see, from here I can just replace. I'll write in terms of VCM the whole expression. So omega I have to replace. So omega will be actually from here. Omega will be VCM by R. So you look this, I can write as half m k square into VCM square by R square, plus this is half m VCM square as we had COM or same thing. Okay, this is the one. So let us take half m and VCM COM square common. So you get k square by R square here, and you get here as 1. So this is how we can calculate. So if you know the linear velocity of the center of mass, and if you know the radius of gyration for a particular object, okay, and the radius is given, then with this actually you can find out the kinetic energy. And look, this particular thing we will be able to use in case of numerical problem. While, okay, I'll just take up one simple problem, or yeah, just simple problem to conclude with. Suppose, so what we have got, see, total kinetic energy we used to get, so half m VCM square into 1 plus k square, that is radius of gyration square by R square. It is the true radius or the distance from the axis of rotation to the mass distribution. Okay, so now suppose I have an object which is rolling down an inclined plane. Suppose there is a, there actually you will be given various objects, and you will be asked to find out what is the time taken or which one will be moving faster and etc. Okay, suppose there is an object, I'm just taking a sphere or whatever, maybe just take a general one, and this has this height h. Okay, then you have to find out when it reaches to ground what will be the velocity. Okay, so we know the kinetic energy will be, the whole kinetic energy will be converted when it reaches here. Okay, so the kinetic energy over here is mgh. Suppose this object has mass m, so mgh will be equal to half m v c m square or com square, whatever you can write. This is k square by, actually I'm accustomed to write VCM, so that's why every time it is happening like this. Okay, look here, from here I can find out what is the velocity over here. If you start with rest, then when rolling down over here up to the ground, what will be the velocity of the object? So object will be having velocity VCM, or maybe we'll write simply V square is equal to 2 into g into h over 1 plus k square by r square. Okay, this is very useful expression for velocity. If I just write only velocity, so it will be square root of this. Okay, this is very useful formula for comparing which one. Suppose you will be given hollow cylinder. Okay, hollow cylinder, sometime you will be given a disc. Okay, disc, then maybe a sphere. Okay, so all types of like rigid bodies will be given, and then they are rolled down this inclined plane. Okay, roll down this inclined plane. So which one will be coming down faster? So from here you can find out this depends on this particular factor alone. What is this? This one. So radius as well as this k, radius of gyration. It depends basically on this particular factor. Okay. So now you can just find out various numerical problem from our quiz set already had been uploaded maybe in our site, so you can just go and practice this kind of like problems related to this particular topics we have covered today. So with this I'll stop it here. So thanks for your patience. So bye for today.